The first plasma loop comes off the corona cleanly. The magnetic field lines guiding it hold their geometry exactly as modeled. The collection vessel at the anchor point reads nominal flow. The extraction team's instruments show a smooth, continuous thread of ionized stellar material being drawn away from the Sun's outer atmosphere and directed into the processing infrastructure overhead. Every parameter is within tolerance. The operation is working. 27 minutes later, inside the stellar core, the gravitational signal from the removed mass arrives. The core does not receive a notification. It does not assess the situation. It responds immediately, automatically, on the timescale set by the physics of a self-compressing nuclear fusion reactor, whose pressure balance has just been told by gravity itself that the weight above it has changed. The star that a Type II civilization proposes to mine for raw materials is not a reservoir waiting to be tapped. It is a self-regulating nuclear fusion reactor whose interior responds to any significant mass change in 27 minutes with a pressure pulse that can exceed the structural limits of any material the civilization has built in the surrounding system, arriving at inhabited planets before any warning from the extraction site can reach them. The 27-minute number is not a safety margin. It is the deadline between the extraction event and the point at which every decision available to the engineering team becomes irrelevant. Abort the extraction, the mass has already been removed. The gravitational signal has already propagated to the core. The response is already underway. Retreat the infrastructure, the pressure pulse moves outward through the stellar layers at speeds that no spacecraft in the surrounding system can outrun from a standing start in the minutes available. The operation had nominal readings at minute 0. At minute 27, it is no longer an engineering problem. It is a stellar physics event that the civilization watches from inside the expanding radius of its own decision. The precise mechanism by which a smooth plasma extraction becomes that event, the specific sequence running between the extraction site and the stellar core and back to the surface and outward to the planetary system, is what the engineering diagrams showing elegant plasma loops consistently omit. A star is not a hot rock. It is a continuous competition between two forces that have been balanced against each other for billions of years at every layer simultaneously. Gravity pulls every layer inward toward the core. The energy released by nuclear fusion in the core pushes every layer outward as radiation pressure and thermal pressure. At every depth inside the star, those two forces are precisely matched, not as a coincidence, but as a consequence of the feedback loop that enforces the match. If the core compresses slightly, the fusion rate rises, pressure increases, the outer layers expand, the core cools, fusion rate falls, the layers contract again. This oscillation runs continuously on a cycle of minutes to hours, self-correcting, never drifting permanently in either direction. Remove mass from the outer layers and gravity decreases. Less weight pressing inward means the core expands slightly under the reduced compression. The fusion rate drops as the core cools. Radiation pressure falls. The outer layers, no longer fully supported by the reduced pressure from below, begin to fall inward. That infall recompresses the core. The compression raises the fusion rate sharply, not gradually because the core has been accumulating a deficit during the period of reduced pressure, and the infall delivers that deficit as a sudden mechanical loading event. The fusion rate spikes. The radiation pressure spike is not proportional to the original perturbation. It is amplified by the same feedback loop that normally keeps the star stable, now running in the wrong direction. How large that spike is depends on how much mass was removed, how quickly it was removed, and whether the removal was symmetric across the entire stellar surface. A small, slow, symmetric extraction allows the feedback loop time to find a new equilibrium and settle there over a period of hours. A large, fast, or asymmetric extraction produces an overshoot. The core fires harder than it needs to for the new equilibrium, the outer layers are pushed outward past their new equilibrium position, they fall back, the core fires again, and the star begins to oscillate through a series of expansion and contraction events. Each oscillation carries energy. If the oscillations damp out, the star settles at a new equilibrium. If they do not, if the perturbation was large enough or asymmetric enough or fast enough, the oscillations grow, and the energy that drives them is drawn from the same fusion reactor that the civilization was trying to harvest. The most energetic version of this instability is a structural failure in the stellar outer layers, a starquake, where the pressure pulse from a compression event exceeds the mechanical strength of the material in a particular layer, and that layer ruptures discontinuously rather than yielding smoothly. The energy released in that rupture is not released as heat to be managed, it is released as a coronal mass ejection, a directed pulse of plasma, radiation, and charged particles that expands outward from the stellar surface at a significant fraction of the speed of light. In 1998, a different kind of stellar structural event was recorded by multiple orbital observatories. The object was SGR 1900+14, a magnetar, a neutron star, an object far smaller and denser than a main sequence star, with a crust under extreme internal pressure. A sudden reconfiguration of that crust, a starquake driven by accumulated internal stress, released a gamma-ray burst in a fraction of a second. The burst was energetic enough to measurably affect Earth's ionosphere, partially ionizing the upper atmosphere at the altitude where radio communication signals propagate. The distance from SGR 1900+14 to Earth is approximately 20,000 light-years. 20,000 light-years. The event that partially ionized Earth's upper atmosphere occurred on the far side of the galaxy. What a comparable structural event in our own Sun, an object 8 light-minutes away, not 20,000 light-years, would deliver to the inner planetary system is not a measurement problem, it is a geometry problem with a known answer. 8 light-minutes is the distance from the Sun to Earth. A coronal mass ejection produced by a starquake expands outwards at a significant fraction of the speed of light. A warning signal sent from the extraction site at the moment the starquake begins also travels at the speed of light, but from a point that is already inside the expanding shell of the ejection. The warning and the leading edge of the ejection depart from the same region of space at approximately the same moment. The warning travels at exactly light speed. The ejection travels at a fraction of that. The warning arrives at Earth before the ejection, by a margin that depends on how fast the ejection is moving, seconds to minutes at most, not hours. Not the days that emergency evacuation of a planetary surface requires. The inner planetary system does not receive a warning that allows response. It receives a warning that allows awareness of what is arriving behind it. The engineering answer that the starlifting literature reaches for is uniform extraction. Distribute the mass removal symmetrically across the entire stellar surface simultaneously so that no asymmetric gravitational perturbation is created, so that every point of the stellar interior experiences an identical gradual reduction in overlying mass, so that the feedback loop can find a new equilibrium smoothly rather than oscillating through it. The physics of the approach is sound. The perturbation from symmetric extraction is genuinely smaller than from asymmetric extraction, and a symmetric reduction distributed across millions of square kilometers of stellar surface allows the star more time to re-equilibrate with each incremental mass removal. Building a field infrastructure capable of executing symmetric extraction across the entire stellar surface requires enclosing the star before extraction begins, not partially enclosing it. Enclosing it, because a partial enclosure creates the asymmetry that the uniform approach is designed to eliminate. Any region of the stellar surface not covered by the extraction field is a region where mass is not being removed while adjacent regions are, producing exactly the differential gravitational perturbation that drives oscillation. The infrastructure that makes symmetric extraction physically possible is, by its construction requirements, a complete stellar enclosure. A structure that covers every point of the star's surface with active field-generating components, powered continuously, maintained against the radiation and particle flux of the star it is enclosing, and completed before any extraction begins. A civilization that has built a complete stellar enclosure before beginning extraction has already demonstrated the material science, energy management, and construction capacity at a scale that required solving most of the challenges that starlifting was proposed to address. The extraction that provides materials for stellar-scale engineering cannot begin until stellar-scale engineering is already complete. You are the extraction operations lead, 2 hours into what the mission architecture called a controlled demonstration extraction, a proof-of-concept removal of a mass quantity small enough to remain within the star's safe perturbation threshold. The plasma loop is nominal, the flow rate is nominal, the collection efficiency is better than projected. The stellar surface monitoring array is showing the expected minor perturbation at the extraction site, well within the modeled tolerance band. At minute 23, the deep interior acoustic sensors, instruments placed to detect pressure waves propagating through the stellar volume, register an anomaly, not at the extraction site, at a depth corresponding to 60% of the distance to the core. A pressure wave is propagating outward from the core region, larger than the model predicted for this extraction rate. The wave is moving at the speed sound travels through plasma at stellar interior densities. You have, by the acoustic sensor's reading, roughly 4 minutes before it reaches the surface. Your abort option is to stop the extraction. The mass you have already removed is already removed. The gravitational perturbation is already at the core. The wave already exists. There is nothing to abort. The primary proposed mitigation that remains after the symmetry argument runs into its own constraint is rate limitation. Extract at a rate low enough that the perturbation never reaches the core faster than the star's natural slow equilibration processes can absorb it. The natural equilibration timescale for a slow, symmetric perturbation is millions of years, the timescale on which stellar winds naturally reduce stellar mass and the star adjusts without instability. An extraction rate calibrated to remain below the perturbation threshold for that equilibration timescale is an extraction rate comparable to natural solar wind, roughly 1,000,000 tons per second. The Sun contains approximately 2,000,000 trillion tons of mass. At 1,000,000 tons per second, extracting 1% of the Sun's mass, a fraction that would provide raw materials for megastructure construction at civilizational scale, takes approximately 60 million years. A civilization willing to wait 60 million years for its first significant delivery of stellar material does not need starlifting. It needs a different civilization model. A civilization that needs stellar material on timescales relevant to civilizational projects, centuries to millennia, needs extraction rates millions of times higher than the safe threshold. The gap between those two numbers is not a parameter to be optimized. It is the distance between a process that does not perturb the star and a process that does. And everything in between is a different point on a continuum that runs from negligible benefit to fatal perturbation, with no stable middle ground where the extraction is both economically meaningful and physically safe. The ironic structure of starlifting is precise. The primary argument for extracting mass from a star, beyond raw material acquisition, is stellar life extension. A Sun-like star ends its main sequence life when hydrogen in its core is exhausted, and the accumulated helium waste product disrupts the fusion reactions that have kept it stable. Remove hydrogen before it fuses, lift it away from the core region as part of the extraction operation, and the star has more fuel remaining at any given age, extending the period during which it provides stable energy to the planetary system around it. A civilization lifting mass to give its star more time is doing so by perturbing the fusion equilibrium that defines that stability, triggering the oscillation instabilities that can terminate the star's stable fusion phase in minutes rather than in billions of years the helium accumulation would take. The intervention designed to extend the star's stable life is the intervention most capable of ending it immediately. The NASA and ESA helioseismology programs that have mapped the Sun's interior acoustic structure over the past 3 decades have done so precisely because the interior pressure wave behavior is the diagnostic signal for every form of internal instability. The data from those programs describes a stellar interior that is continuously oscillating in thousands of simultaneous acoustic modes. The star is never fully at rest, its surface rising and falling by kilometers in regular patterns driven by the same pressure feedback that defines its equilibrium. Star-lifting proposals that treat the stellar surface as a stable extraction platform are interacting with an object whose surface is already in continuous motion, driven by interior pressure waves, with a dynamical response time of 27 minutes to any significant change in the mass that those waves are propagating through. SpaceX, NASA, and every other organization currently planning missions to the outer solar system treats stellar perturbation as a background hazard to be managed. Solar flares, coronal mass ejections from natural stellar activity, proton events that require spacecraft shielding and mission timing. The activity of a sun whose hydrostatic equilibrium has been perturbed by an extraction event at rates necessary for civilizational-scale material acquisition is not an enhanced version of natural solar weather. It is a different physical regime, driven by the same feedback loop but running in a direction and at a rate that the geological record of the solar system has no precedent for, because the solar system's geological record was produced by a star that no civilization ever attempted to mine. The diagrams show the plasma loop, the elegant arc from corona to collection vessel, the smooth flow rate, the nominal parameters at every sensor point. What the diagrams cannot show, because they are drawn at the scale where the Sun is a small circle, is the 27-minute clock running in the stellar core from the first extraction event, ticking at the rate set by stellar physics, indifferent to the nominal readings on the extraction team's instruments, ending at the moment when the pressure pulse it produces makes all of those instruments the last measurements they will ever take.